Good morning, everyone. I'm Phương Pham. Welcome to the course Food Waste Management. This is the second practical activity of the study unit, and it belongs to the second module, Food Waste Prevention and Reduction Strategy. This practical module focuses on identifying and preventing food waste across interconnected stages of the food supply chain, from production until consumption. Through real-life scenario, you will analyze the underlying cause of food waste, which could be technical, organizational, and behavioral factor, and propose targeted prevention strategy at multiple stages of food supply chain. With root cause analysis and solution design, you will develop system thinking skills and learn how prevention measures can reduce waste more effectively than downstream management. This practical activity helps you strengthen analytical reasoning, enabling evidence-based decision making, and prepare you to design practical, stage-appropriate food waste prevention strategy in real-world context. At the end of this activity, you will be able to apply prevention strategy across multiple stages of the food supply chain to reduce avoidable losses. The exercise of today is about food waste prevention in a canned tomato production plant. So the scenario is a medium-scale canned tomato processing plant produce peeled tomato packed in metal cans. The production process includes several steps: sorting, washing and trimming, then blanching and cooling, peeling, and packaging. And then we have thermal treatment, which is sterilization, cooling, labeling, and finally storage. A recent food waste analysis identified two major waste hotspots at packaging and sterilization stages. Significant quantity of finished or semi-finished products are discarded at these stages due to quality and safety non-compliance. So at this point, we can assume that the identification and also quantification of waste were already done. The waste at each stage are determined as follows. At packaging stage, the waste is overfilled cans and leaking or poorly sealed cans. And then at sterilization stage, we have under-sterilized cans and the waste that weren't batches discarded due to monitoring failure. The plant management team want to prevent food waste from occurring rather than manage or reduce waste after it's generated. So the tasks are identify the most likely cause of food loss or waste at each stage, and for each cause identified, propose prevention strategies that address the root cause and avoid waste generation. To carry out these tasks, I want to suggest you a procedure. The first step is perform a root cause analysis using the fishbone diagram. The template of this diagram is provided in the manual. You have to use the fishbone diagram for each waste. So here in the exercise, we have four types of waste. For this reason, you need four fishbone diagrams, each diagram for a type of waste. For each category of cause, identify potential technical, organizational, or operational causes that contribute to waste generation. The next step is select the key costs to address. You have to review the identified costs and select those that are most significant or directly linked to the waste generation. And then you focus on the causes that can realistically be addressed through preventive action. The next step is propose a prevention strategy. So for each selected cause, you have to propose prevention strategies that are upstream, aiming to avoid the generation of food waste. Attention, at this step, we have to find a way to avoid the waste and not to minimize or handle the waste after it's been created. The last step is summarize the findings. You briefly summarize the main cause of food waste identifies and corresponding prevention strategy. Also, you have to highlight how this action contributes to reducing food waste across the system. For the data collection, firstly, that's an important thing that the effective identification of cause of food waste requires the use of relevant information that describe how the process operates. Before filling the fishbone diagram, you should consider available information about the process, such as process description, operational procedure, and equipment characteristic. This exercise is about a process in the processing stages, so it's actually a little bit complex. The objective of this step is not to measure waste quantity, but to gather sufficient information to support structural root cause analysis and the identification of appropriate food waste prevention strategy. So this is the template fishbone diagram. You can also find this diagram in the manual. There are six main categories of cost, which include methods, machine, people, which could be employee or consumer, depending on the context, materials, measurement, and environment. Let's solve this exercise together. We start with the first step, which is the identification of cause. It includes here you can apply the first and the second step in the suggested procedure. The first loss is overfill can. You can fill all of this information in the template of fishbone diagram, but here I will only list the category for convenience. In the method category, the cost could be filling procedure not adapted to product variability, no standardized start-off or changeover protocol, excessively high fuel speed related to product flow stability. In the machine category, we can have a cost of waste, which is the fuel calibration differ over time. The calibration of machinery doesn't stay the same over time. For this reason, we need maintenance. Material category contain variability in tomato size and liquid viscosity. Product temperature fluctuation affecting flow rate. In the people or employee category, we have manual adjustment are not consistent between operator or a limited awareness of how small deviation can affect the fuel weight. In measurement category, we can have insufficient regular checks a fuel weight or deviation detected only at the end of the line. Environment category include high production pressure, encouraging operation at maximum speed, and for this reason it can cause errors. Still in the packaging stage, we have the loss that's caused by leaking or poorly sealed cans. In method category, it includes incorrect seam setup after changeover and no standardized seam inspection planned. About the machine category, it could be worn or misaligned seaming roller and chucks, inadequate maintenance or seaming heads. In material category, we have can or lead incompatibility. So this is about the design of the material, of the packaging material. In a people category, there could be insufficient operator training on seam quality and delay reaction to early seam defect signal. The measurement category include lack of inline seam monitoring and finally environment factor contain high humidity or products plastic that contaminate the seams. Now we move to the sterilization stage. Here we have the loss of the under-sterilized cans. So you know that the sterilization is needed to maintain the safety of the product. If the can under sterilized, the food safety is no longer guaranteed. In method category, we have incorrect sterilization recipe for product and can size. Not standardized retort loading patterns. For the machine category, we have uneven heat distribution in retorts. Retorts performance drift due to steam or circulation. In material category, there could be product density and composition variability, or different can size treated with the same parameter. So, if the can has a different size, for example, it's bigger, maybe they require a longer time achievement. For example, in people category, we have incorrect sterilization recipe selection, error during retort loading or cycle initiation. Measurement category include inaccurate or uncalibrated temperature sensors or lack of real-time deviation alarm. And finally, environmental factor include high throughput pressure, discourage cycle interruption. For example, maybe the employee had noticed something is wrong, but the processing speed is very high and they don't want to stop it. The second waste of loss of this stage is one batches discarded due to monitoring failure. So when the plant is unsure about the safety of a batch, it's better to discard the entire batch. It's better safe than sorry. In method category, we have inappropriate documentation process. In machine category, there could be data logger or recorder malfunction. Insufficient critical monitoring device also. Material factor include label or batch ID not correctly linked to the recorder. People factor include incomplete record checks by operators and errors during ship handover. In a measurement category, we have missing or incomplete time temperature record and no automatic data validation. Environment category include temp pressure leading to skipped documentation. After the identification of cause of waste for each loss, now we have to find a solution for each cause of waste. Firstly, we start with the first loss, which is overfill can during packaging stage. For method category, filling procedure not adapted to product variability. We can standardize filling procedure for different product characteristics based on viscosity or temperature. If there's no standardized startup or changeover protocol, we can develop one, including first scan approval before full speed production. Then, for excessively high fuel speed relative to product flow stability, we can adjust and cap minimum fuel speed according to product flow stability. In this way, the fueling error are avoided by stabilizing procedure before product began. For the cost that fuel calibration derive over time, we can implement a routine fuel calibration plan or introduce automatic correction mechanism where possible. For example, fuel feedback from inline controller. In this way, equipment drift is prevented before it leads to systematic overfilling. For the cost of waste material category, we can control product temperature and viscosity entering the field. So it's actually an inline control. And then we can introduce a specification or blending strategy to reduce the variability in tomato size and liquid consistency. This solution can help reduce the fuel variability. About the people category, we can train operator on the impact of small adjustment on fuel weight or limit manual adjustment by defining acceptable parameter range and standardized setting. With this solution, we can reduce operator-related variability. For the measurement category, we can increase the frequency of inline fuel weight checks or implement real-time alarm when fuel weights approach a tolerance limit. In this way, the deviations are detected and corrected before non-compliant can are produced. About environment factor, in which high production pressure encourage operation at maximum speed. We can use balanced production targets with process stability indicators and introduce a performance metric that prioritize process control over maximum speed. So the quality is always preferred over the speed of production. We can reduce the production pressure to avoid unstable operation with this solution. For the leaking or poorly sealed can, considering the method category, we can standardize the steamer stand-up procedure after changeover with documented target parameter or define and implement a seamless inspection plan with fixed frequency and acceptance criteria. So in this way, incorrect setup are avoided before defective steam are produced. For the machine category, we can apply preventive and predictive maintenance for seam head, roller, and chuck. In this way, we can avoid the unexpected downtime and the error like leaking or polyseal can, as we are analyzing. We can replace critical SIM components based on usage rather than failure. So the maintenance should be done before a failure occurs. With this solution, mechanical cause of SIM defect are eliminated proactively. For material factor about the can or the lid or the variability of the lid quality, we can verify compatibility of can and lid through incoming quality checks. So it means a better quality control about the packaging material. Or work with supplier to reduce variability in dimension and quality. So with this solution, unsuitable packaging material are prevented from entering the process. About the employee factor, we can train operator to recognize the early signs of SIM defects or define clear responsibility for SIM quality checks and escalation. Human response to SIM issue become timely and consistent with this solution. For the measurement, we can introduce inline SIM monitoring or frequent teardown inspection, or use the trends analysis to define gradual SIM degradation. In this way, SIM defects are detected before large volumes are affected. For the problem of high humidity or product splashing, we can control humidity and reduce product splashing in the seaming area. Improve cleaning and housekeeping around the seam formation points. With this solution, environmental contamination of seam is avoided. Now we are going to analyze the solution for the sterilization stage. For the under-sterilized cans problem, about considering the method category, we can apply the validation of sterilization recipe for each product type and can size, or standardize a retort loading pattern with clear limit and diagram. With this solution, incorrect process design is eliminated before production. For the machine issue, maintain return to ensure uniform heat distribution, or implement preventive maintenance for steam supply, vents, and circulation system. In this way, equipment performance remains stable during sterilization. For material category, we can control product density and composition before sterilization and separate the processing condition for different can size and different products. In this solution, heat transfer variability is reduced. For the people factor, like incorrect sterilization, recipe selection, or error during retort loading or cycle initiation, we can train operator on correct recipe selection and loading procedure and use checklists for retort loading and cycle initiation. So with this solution, we prevent human error during critical steps. For measurement factor, we can calibrate temperature and pressure sensor regularly, so regular maintenance. Install real-time deviation alarm with defined response action. The deviation for this reason are detected immediately and corrected. For the environment factor, like high throughput pressure discourage cycle interruption. We should empower operators to interrupt cycle when deviation occurs. This is also a practice of Lean Six Sigma. Align production targets with food safety requirements. So the safety is prioritized over throughput or production speed. Now we are going to analyze the solution for the last loss, one batch discarded due to monitoring failure. For the method issue, we can replace manual documentation with standardized validate electronic procedure. Introduce a mandatory document verification step before batch release. In this way, documentation failure are avoided before batch disposition. For the machine category, we can use a reliable data log with redundancy for critical parameter and schedule regular verification for recording device. With this solution, we prevent the loss of data monitoring. For material problem, we can improve batch identification and labeling system to ensure traceability and link label automatically to electronic process record. With this solution, batches can always be matched to valid record. About the employees, we can train staff or operator on the importance of complete and accurate record and standardize shift handover procedure with documentation check. So the human relay documentation error are reduced. For the measurement category, we can implement automatic data validation and completeness check and audit record regularly to identify gaps early. With this solution, the basic data are detected before product disposal is required. For the environment factor, like time pressure leading to skipped documentation, we should allocate sufficient time for documentation activity and reduce time pressure during critical recording step. In this way, documentation is complete correctly even under workload pressure. So we have just concluded the practice of root cause analysis and finding the solution for waste prevention in the scenario of tomato processing plant. It is actually a little bit long and complicated, but once you address the root cause, you can minimize the probability of waste generation. Thank you for your participation. I hope you can apply this approach whenever you have a problem to resolve. Goodbye and have a nice day.